Hello everyone, today we're going to be covering another trick you can use to solve some AMC problems, and this one involves perfecting the square. I'm not going to be covering the details of perfecting the square, this process itself. I'm just going to dive straight into how you can use it to solve some AMC problems. So first up, as an example, let's suppose that you see this question on the AMC. So it says, find the minimum value of x squared plus 5x plus 3, where x is a real number. So this is a relatively easy problem if you know what you're doing, but I'll just use this as an intro into how you can use this to use perfecting the square to solve this kind of problem. So, well, as hinted, a good method to use is let's perfect the square here. So we have x squared and 5x, and if we want to perfect the square, we know that we would want x squared plus 5x plus 5 over 2 all squared, because this part here would be equal to x plus 5 over 2 all squared. Now, obviously, this part here isn't equal to 3. And so we want to account for this. We want this expression here to be equal to this expression. So we need to adjust this by a constant. And this constant would be 3 minus 5 over 2 squared. And this would simplify to negative 13 over 4. So by perfecting the square for this expression here, we get x plus 5 over 2 all squared minus 13 over 4. Alright, I'm going to erase all of the workings down here. And the next step is to say, okay, so we want to find a minimum value of this quadratic expression. And we've written it in the form of a square minus a constant. Well, there is a very important fact to be noted here, which is if you have anything, a, where a is real, then a squared is greater than or equal to 0. Because if a is greater than 0, then naturally a squared is greater than 0. If a is 0, then a squared is 0. And if a is less than 0, a squared, the negatives will cancel out. And so a squared will be greater than 0. And so it doesn't matter what a is. If a is real, then a squared is greater than or equal to 0. That is always true. And we can apply this fact up here because we have a square here. We can replace a with x plus 5 over 2 because we have this given condition here that x is a real number. So we have that x squared plus 5x plus 3, which is equal to x plus 5 over 2 all squared minus 13 over 4, is greater than or equal to 0 minus 13 over 4, because the square is greater than or equal to 0. And this is equal to negative 13 over 4. Alright, so now we have an inequality, and this is what we want. We've shown that x squared plus 5x plus 3 is greater than or equal to negative 13 over 4. And we have one last step to do, and that is to show that this value here, negative 13 over 4, is actually achievable. because if it isn't achievable, it means that our minimum value isn't actually negative 13 over 4. We'll have to dig deeper. But perfecting the square gives us a really easy way to see if we have found a minimum value. Because if we have in here x plus 5 over 2, we know that when we plug x equals to negative 5 over 2 into this quadratic expression, we're going to get this square here equal to 0. And so this is a really, really easy method to see the minimum value of this and to show that this minimum value is actually achievable for a certain value of x. So in conclusion, the minimum value of this quadratic is negative 13 over 4, and it is achieved at x equals to negative 5 over 2. So this point here, negative 5 over 2, comma, negative 13 over 4, is essentially the vertex of the quadratic, you can say so. Alright, so now we're going to move on to an actual question that involves this technique. Alright, so it says find the minimum value of this real value function f x comma y equal to x squared plus 2xy plus 3y squared plus 2x plus 6y plus 4. So we want to complete the square for this one as well. And it's as you can probably tell, this is going to be more complicated than our first example because we have y's in here in addition to x's. And first thing that I notice is that there is a 2xy in here. And so this means that there must be a square of the form ax plus by plus c squared. And this is because if I don't have this kind of square and I only have ax plus b squared something something plus, cy plus d squared, or the x's and y's are always separated, I'm never going to end up with a factor where x and y are multiplied together. So I know that I will need to have a factor with this form, ax plus by plus c all squared. So something really natural to consider is, since the coefficient of the xy term is positive 2, we're inclined to write x plus y all squared, because x plus y all squared is equal to x squared plus 2xy plus y squared, which is exactly what we want for the xy term, and also is exactly what we want for the x squared term. So that is really nice. But the y squared term is different. Essentially, we even after we consider this square here, we would still have left 2y squared plus 2x plus 6y plus 4. So what do we do next? Well, I suppose we haven't finished considering this factor yet, because we haven't included a constant term. Remember that originally my assumption is that we're going to have a factor of this kind, and right now I'm assuming that c is equal to 0, but that's not necessarily the case. So what can we say? Well, now I notice that there is a plus 2x over here. That gives me the indication that there probably is a x plus 1 squared in here, because x plus 1 squared is x squared plus 2x plus 1, and this will account for the 2x term. But unfortunately, we can't have both of these. And the reason is, if we have an x squared here and the x squared here, things aren't going to work out. We have too many x squared. But there is another way around this, and that is by combining these two in a clever way. X plus y plus 1 all squared. So what does this give us? This would give us x squared plus 2xy plus y squared plus 2x plus 2y plus 1. You can expand this out and you can double check that this is indeed the case. And let's see if this will work. So I'll erase everything else, but leave the x plus y plus 1 all squared. So what do we have left? Let's take note. We have 2y squared plus 4y and plus 3. So now we see, okay, this is also really close to being a perfect square, or actually 2 times a perfect square. It will be really nice if we can write y squared plus 2y plus 1, and we can double it so that the coefficients for the y squared term and the y term match up. But we see that this red thing down here is 1 less on the constant term. Well, no worries, we can simply add 1 at the end. And so we see that this blue thing is actually equal to 2 times y plus 1 all squared plus 1. So I suppose now we have completely perfected the square for this. And let me just clean this board up a little bit. Alright, so this is what we've got so far. I've rewritten everything and cleaned it up. And if you want to go back and analyze this, you can pause the video here. So again, similar to the example, the very simple example that we did earlier, over here we want to find the minimum value of this function. And we have 2 squares and a constant. So immediately we can say that this is greater than or equal to 1, because the minimum value of these 2 squares is 0. So now we have to show that this minimum value is actually achievable. Essentially, we want to show that it is possible. I'll actually write this on another page. So we want to show that it is possible to have x plus y plus 1 is equal to 0 and y plus 1 is equal to 0. Well, let's solve the second equation first. That's really simple. Y is equal to -1. And we very quickly see that we can plug this back in to see that x is equal to 0. And so when x comma y is equal to 0 comma -1, these 2 squares here are indeed equal to 0. And so this minimum value of 1 is actually achievable. And so the answer to this problem is 1. Alright, so we're going to move on to another problem. This problem thankfully does not have multiple variables multiplied together. And so if we want to perfect the square for this problem, it's going to be relatively simpler than the last problem. But this is really weird because we're given one equation of 4 variables, and we're asked to find a specific value here, as if we're supposed to know what A, B, C, and D are supposed to be. And spoiler alert, we do have to find what A, B, C, and D have to be. There is no other clever way we can relate this equation to this expression here. We'll just have to find what A, B, C, D are. So one method we can do this is by perfecting the square and see what happens. And you'll see what I mean after we've perfected the square. So first, we want to write this as a sum of squares. So let's consider each of the variables separately. We have a squared minus a, 3b squared minus b, half c squared minus c, and 3 over 2 d squared minus d. And we're going to figure out what this constant term is going to be at the end. So right now I'm not really caring about this -1 here. Alright, so we want to perfect the square for each of these 4 variables. First, for A, we find that this has to be 1/4. For B, this has to be 1/12. For C, this has to be 1/2. And for D, this has to be 1/6. You can go ahead and double check by yourself. And now we want to write this as squares. So this will give us A minus half squared. This will give us 3 times B minus 1/6 squared. For C, we'll have half times C minus 1 squared. And for D, we have 3/2 times D minus 1/3 squared. And finally, let's consider what the constant term is going to be. So we have here 1/4 plus 1/12 plus 1/2 plus 1/6. And so if we consider all of these and we add all of these up together, we get 1. This is actually really good because over here we have 1. It is -1 over here, but when we rewrite everything, we're going to see that this is actually really good because this number here is exactly what this number is here. So let me clean up the board and I'll get you back in a second. So after completing all of the squares for all 4 variables, we're left with this equation. And now you might be getting at what I meant when I said that there might be some kind of constraint on this. Because as you can see, the left-hand side are completely composed of squares. We can represent the left-hand side as a squared plus b squared plus c squared plus d squared. So this is kind of the general idea of what the left-hand side looks like. And the right-hand side is just 0. So we have a really, really big constraint here. If we have a sum of squares, and this sum is equal to 0, well, each of these squares can't be negative, which means that all of them has to be 0. So if we ever end up with an equation where it is a sum of squares, and it is equal to 0, we can immediately conclude that all of these terms within the squares are zeros. And we can use this fact here. Essentially, what we have is that a minus half is equal to 0, and b minus 1/6 is equal to 0, and c minus 1 is equal to 0, and d minus 1/3 is equal to 0. So now we have what a, b, c, d are. A is equal to 1/2, b is equal to 1/6, c is equal to 1, and d is equal to 1/3. And voila, we can go back and find what 1000a plus 100b plus 10c plus d is equal to. And if you go back and calculate, you will find that the answer is 527. So this is the final answer to this question. And this concludes our discussion today on how to use perfecting the square to solve problems where you want to minimize or maximize a function, where you're given fewer equations that you're expected to and you're asked to find a specific value. And it can come in handy even when you don't know it. So thank you for watching, and I'll see you next time.